biologist. I don't want to reverse engineer a brain. I don't understand the brain. And actually, I don't want to understand the brain. First of all, let me thank Stuart and you too for the invitation, because it's very inspiring. I might go home after these 2 days and thinking, well, maybe I should start doing something completely different. So what I will do is indeed I'm a physicist, and I like to first tell you why I started with this bits and brains idea, and trying to get some people around me that probably know more and can do more about this together with me to work on this. So I'd like to give my motivation, and then to give some credibility. First, we'll show a few things that have very little to do with it, but actually led myself in working on, indeed, ways of energy-efficient storing of information that finally brought me to this idea. And so we'll see what this will lead to, and that at the end it will mostly be some sort of ideas that we have and concepts rather than many nice results that I have already seen coming by today. So what we are actually, indeed, in my group is actually known for, that is like that we are looking at magnetic storage, actually at magnetism on a very short time scale. And what that exactly is, I'll show you in a moment, but I'll first give you my motivation. And that is indeed that if you're looking at the current development with data, we are all generating. I mean, I've seen the peta, exa, and the enormous numbers that have been coming by. And that is actually indeed something that is happening in less than the last decade. And so that has to do with the fact that all this big data, this enormous amount of data that we all produce, with the social networks, with the Google, with internet, and we make pictures and immediately send it around to all our friends. We have lots of friends. We don't even know that they are friends when they share it with their friends, etc. And so this goes extremely. A nice way to demonstrate that is actually this. Maybe some of you know this. This is just a picture of some event. It was in Europe. And this was in more than 10 years ago. This was 12 years ago. And then for some particular reason, this event was repeated sometime later, only in 2013, so 4 years ago. And there was a pointer here, but I mean, I can point out the difference, right? There's one person here with a cell phone that makes a picture, and all the others in the 2013, nobody's actually looking at the screen anymore, but only on their own screen. And yeah, thanks. So everybody is looking what's happening. This is indeed, it is the same happening, but now, okay, this is, I think, there's only one picture, but you get the gist of what this enormous increase of data. And you can really see that is really starting, less than a decade ago. And this is enormously exploding to the fact that right now, on average, we have more than a device per person worldwide, but that's average over all people. And as we know, there's lots of us that have maybe 4 or 5, and still several billions of people have maybe few or 0, but that will not stay like that. And we cannot say, well, this costs too much energy, so we should not do that. So this is not going to stop. And it's interesting also to see that if you think about Moore's law and everything, that things were always becoming smaller, including the cell phones. But now they're becoming larger again, and that has to do with the functionality. When I'm showing my cell phone, it says, well, you can actually also, did you know that you can phone with it? But because that is sort of sometimes forgotten, because we use it so much more for all the other functions it has. And a good example is the following. Anybody, also myself, if I have to go to a new place, I just Google how I have to travel, right? And so I find this. But, well, you know that 30 of these Google searches takes enough energy to boil a liter of water, to bring a liter of water from room temperature to boiling. Well, that's 30 searches. Well, there's more than 3 billion searches per day, all of us. Huh? And so this is basically really where all these enormous data storage centers come from, and they already now use more than 5% of the worldwide electricity. So this, indeed, is sort of what inspired me to think about, well, we have to find better ways, because this is growing. This is exponentially growing, this amount of data. And so on the one hand, like here in Germany, lots of solar cells, windmills, etc. We're working very hard because we know energy is an important problem. And at the same time, many of us, even here, don't realize that we're creating this enormous energy problem at the same time. And so I was surprised, actually, when I started thinking about this, and then it looked so obvious. And of course, certainly people in the industry are aware of that, but a lot of us colleagues weren't. So now, to think about how, if you're just looking at the history, I've seen some history coming by, so I thought, okay, I can also do that, but not in biology, but in solid-state physics and in technology. The enormous, let's say, development in computation is, of course, after the bulb, the tube, was indeed replaced by a transistor. Of course, the first transistor didn't really look likely to do that, but very, very quickly it was realized that one of the major things with a transistor is that you can make it in such a way that you can scale it. And this scaling has been tremendously successful. And actually, today I realize actually that probably because it has been so successful, nobody ever thought about other ways of doing computation than indeed as was sort of thought of in very early times in the von-Neumann architecture, because the scaling was so efficient. And so it doesn't matter, the speed and everything improved so fast that, I mean, this is one of the examples of the very first computers. And this is an example of present-day computers, which are much more powerful than the early ones. And indeed, this is all a result of scaling. But we all have learned that indeed there is a problem with this scaling. Not so much because industry cannot make things smaller. I'm very proud one of the few real industries we still have in the Netherlands is ASML, who makes all these lithography machines. They can do it, but that's not the point. The point is indeed that the power consumption. Because these structures become so small, half of the current goes away in leaking currents, and that means half of the energy, more or less, is wasted. And that is a problem. There's roughly sort of, you can make things smaller, but not better. I can show another graph, and that is, for instance, at the clock speed. And the clock speed has not, we saw the clock speed today at one of the slides, or on others, it's about 3 gigahertz. And the reason, well, it was already 3 gigahertz almost 8 years ago. The reason that it doesn't change is indeed because then they would all burn our chips. So we have to limit that. And so so this is one of the really big problems. And this is interesting to see. This is actually the end result of a little movie, but I'm always skeptical with movies, because if I put a movie, then my laptop stops. But this is basically, if you take the cooling of this chip, it takes less than a few seconds and it goes up in smoke. And now let's look at storage. Storage has gone actually in the same way as the processor through this enormous scaling. This is one of the first hard disks that has an impressive capacity of 5 megabytes. and took a plane to ship it. And if you think about, and now I'm coming a bit closer to home, magnetic storage these days, and actually from the very beginning, because we're talking about storing zeros and ones, magnetic storage has always been very effective because a magnet has a magnetization up and down. And, but that costs about 0.1 nanojoule right now in present day technology. And this 0.9 nanojoule is thus indeed to bring let me go one back first. So to, to reverse one bit to the opposite. That is, now that 10 minus 10 joules sounds very small, but as I already indicated, we generate so many bits that this is already now causing a serious problem as far as energy is concerned. Now, as a physicist, you can look at it and then you think, well, what is the energy requirement? And then, well, this is basically, well, fortunately, there is an energy barrier between up and down, because otherwise it would flip all the time. And this energy barrier is for, let's say, if you want to have storage which stays at least about 10 years, the standard is about, well, this should be about 60 kT. But 60 kT is only 10 minus 19 joule. So that's actually very promising, because that shows that actually if we are smart enough, then to do that, we can gain a lot. Because right now we're doing it at this level, so there's almost 10 orders of magnitude to be gained. And as I already indicated, it is important that we gain some orders of magnitude. So then I will very briefly show what maybe can be done before I'm going to our brain-inspired work. And that is manipulating spins. But because how do we do this normally? Normally, you do that with a magnetic field. So we have an effective magnetic field that is given by, well, an applied field, but also by interactions with a lattice, that is the and the spin lattice relaxation, and also with the other spins. And now, usually you apply a magnetic field, and then you can change the orientation. Now, let's, the best way to do that is because it's a precessional motion, so it's a torque, so the best way to do that is apply always a field perpendicular. But so what are the typical fields that people use? Now, typically, of course, normal magnets and also magnets that are in a present-day hard disk drive is something in the order of between 0.1 and 1 Tesla. That is sort of the, also the typical, let's say, refrigerator magnets are, let's say, less than a Tesla, but they're not that weak. Then you can go to stronger magnets, superconducting magnets almost go up to 20 Tesla these days. And then you can come to Nijmegen. We have a high field magnet lab, and we have very strong magnetic fields, well, at the moment up to 38 Tesla DC. Next year, hopefully 45. But then if you think about it, if you think about internal fields that are, let's say, related to the spin-orbit interaction, that is basically the strongest fields that we can make in the lab. But if you think about the effective field that spins feel, that is the exchange interaction, then you're talking about fields of 100 to 1,000 Tesla. These are enormous fields. You can find, yes, you can find in the stars, but not really but they're there in the material. So the idea is, like, can't we exploit these strong fields one way or another and use that to our advantage to indeed switch a magnet. And then here you have the time scales that are sort of related with these strengths. So this is typically, let's say, if you think about let's say, normal fields and magnetization dynamics and precession, then you're talking about sort of nanoseconds, 300 picoseconds. But if you're thinking about very strong fields, then you're talking about sub-picoseconds and femtosecond timescales. And so this is what we started to do. And then the idea is magnetic recording. Normally you do that indeed if it's just coming with a field. You have a short pulse, and then you reverse a bit. And that takes, like I said already, a 0.1 nanojoule and around 1 nanosecond in time. And so our question was then, some years ago, can't we do this much more fast, but also much more efficient using light? And what light should you use then? If you want to, indeed, use light and use the exchange interaction, then you want to have a strong pulse on the order of the time scale of the exchange interaction. And that means sub-picoseconds, femtoseconds. So this is what we started to do. So we took a magnetic disk with this magnetic alloy. It's only 30 nanometers thin, and there's no magnetic field here, so we just put it under a microscope. And, oh, it misses the microscope, sorry. But and then we can look at it. This is, if you look, this is a polarization microscope, then you find this field of view. And what you see there is actually the very large domains for magnetization up or down. There's no magnetic field applied. So that means if you have a very thin film, then, and it's such a, let's say, film of 1 centimeter square, but only 20 nanometer thick, will break up in large domains. And these are the domains that you can then visualize using magneto-optical, like Faraday effect. Okay, so this is the magnetization up or down, and then we indeed are like putting femtosecond laser pulses on that, and then now we move a femtosecond laser pulse through these domains, and then we discover that you can actually indeed use these light pulses to reverse the magnetization, and if you use now the opposite helicity, then here you make everything standing up, and here it goes down. And now these are lots of pulses, 40 femtoseconds, so it's very short, but with a kilohertz rep rate, and it moves slowly, so you cannot see what an individual pulse does. But if you do this now very fast, then you find that you can indeed write individual bits with a laser. And so we use that indeed to write magnetic bits. Now, in the beginning, that was still on an optical length scale. Then we realized, well, if you really want to do something with that, you have to bring it down to the nanometer length scale. Present day, it's like about 50 nanometers. And this was, like say, about 20 micron. I will not go into that, but we have done that. So we have used nano antennas, plasmonic antennas, and we were able to do this whole switching on the 40 nanometer length scale. And as a result, we can indeed be competitive with present-day recording. And then came the following. If you look, I said already, this is sort of what the present-day hard disk drive does. It's about 100 picojoule, 0.1 nanojoule. It takes about, well, 10, effectively, it's in the order of nanoseconds. The solid state is very nice. I don't have a disk drive anymore in my laptop, but it is certainly fast, but it's certainly not energy efficient. So this is certainly, it's very convenient, but it's not something for large-scale storage. And now if we're looking to our way of optical storage, then not only can do this very fast, not on the femtosecond, but effectively on the picosecond time scale, which is already 3 orders of magnitude faster. But the energy per bit now we have brought it down from the nanojoules to the femtojoules. And that was actually sort of a few years ago when I started to think about, wow, so it is possible. And of course, doing this for one single bit doesn't make it into a device yet. But using optics and using, indeed, combination of optics and magnetism, there is a possibility to indeed, well, we are not yet on 10⁻⁹, although very recently we have managed to reach attojoule type of switching in magnetic garnets. But that's nice as a proof of principle. I don't see that really working in any device. But this, in principle, would be possible. So we're actually trying now to put that in a device. So we, not so much in a hard disk drive, because in a hard disk drive, actually, most of the energy still is in the motor. And so in the future, we have to do it differently. Well, the new development is these MRAM devices, magnetic random access memories, and so there's basically nothing moving anymore. And what we're currently working on in a European consortium, so there's a lot of people involved, including IMEC, that can make structures, and people that do photonics, is to have a photonic network together with the MRAM and really make something that might indeed be a proof of principle of a real device and much more energy efficient. We aim at least of 2 orders of magnitude to be a little bit on the careful side. Okay, so much for what we can do, but on the other hand, the reason I'm here is indeed that we all know that we talked about this, let's say, von Neumann bottlenecks and whether or not this can continue. Now we have to do differently. This I already indicated, we also have to do differently. Maybe using optics is one option, but indeed looking beyond von Neumann, well, okay, this I can do fast because this is already indicated. This is why we started thinking about that. Let's look at the brain. And it may be clear from the previous talk, or from my previous slides, I mean, that I don't really know anything about the brain, but I'm here to learn. And, but indeed, we realized this enormous difference from the orders of magnitude, so whether it is 10 or 20, I don't really care, but that it is 10 watt or 10 megawatt, I do care. And so, okay, what I've learned so far is indeed that this indeed can go very fast, but you need it to be very fast because everything is serial. And one thing is that in the brain, things work parallel. And so now the question is, can we now indeed use this sort of knowledge, or, well, this little bit that we know of, or certainly this little bit that I know about how this brain does this, and can we, one way or another, let's say, use that just to be inspired. So I have no notion and no ambition to try to imitate this, but more to see, can we do, well, something more parallel? Can we do something more, let's say, at least more energy efficient? Now, so then, of course, I go back to magnetism because that is the field I know, and I already indicated we only need sort of 40 kT. It's already interesting to see that basically that is already this barrier is 40 times larger than basically in the brain, because that is room temperature. So I'd like to understand how the brain can work with all these very noisy signals. I have no idea, but maybe some of you do. Now, this was already mentioned that indeed there has been an enormous development in what is called, maybe wrongly, but I don't know, artificial intelligence. So using indeed computer programs where the program basically has been in such a way that the program can learn. So what Beth earlier said, the main reason that this AlphaGo program could beat this guy in Go is indeed because this program could learn, and it also could do pattern recognition. There's two things that so far we thought it was very unique for the brain. So somehow in the software you can do that. However, the point is, so you have a program that learns, but at the same time they're still using this supercomputer to do all these calculations. So it's very clever, and I think it's very useful, and it will be, and it is already being used for many, many applications, and certainly in this pattern recognition. Think about security and all kinds of applications. But it's not a way to solve this energy problem that I said in the beginning. So to do that, you should actually be as smart as, let's say, the people in software, but then do it in hardware. And that's basically what we hope to do. So I want this revolution not in software. In software, it's possible, we know this now. And, but now we have to do it in hardware. And so that means really materials that can learn, not a program that can learn. So when I started thinking about that, the first thing is, of course, that I realized that I have no idea. And instead of, I could also, what I should have done, like Stuart here, if you don't have an idea, you just organize a workshop and you invite all people, maybe they can tell you. So I did similar, but I invited all kinds of people around me, like Bert. We have a very active and strong neuroscience in Nijmegen, and extremely good theorist, material science theorist in magnetism, Michel Nelson. But we are also very brilliant theorists like Christiane de Marijs-Smith in Utrecht. Then in Twente, our neighbors, and the Netherlands is small, so it's not far away, you have people that can make all kinds of materials, Dave Planck and Hans Hilgekamp. And so they can come up with the models, maybe with the materials, because there's lots of new materials and possibilities. And actually in Nijmegen, we in our group and also our colleagues, not only myself, we're pretty good in spectroscopy and in analyzing. So I thought if we bring these people together, maybe we can make an attempt. And there are some more people involved that didn't fit all on the slide. So I will just show some sort of first ideas only that we have. And although now after I'm listening, the more pessimistic I become, to be honest, if I listen to the more I learn about the brain that I did this today, but it doesn't matter. So what you want basically is that these neurons, they talk with like per neuron with thousands others, at least maybe 10,000, and these connections are not rigid. It's not like on-off transistors, but these are flexible, plastic. And so that is something that we have to mimic then, if we want to do that. Maybe that's not even the best way to do it, but okay, that's one approach. And so that is one thing. And then the architecture. Then the more, especially since last night already, and also today, the more you learn about the architecture, you think, well, we have to think about really different architecture because I think it's too complex to try to mimic that. But anyhow, the architecture is very clearly very different than what we presently do in our, let's say, computer hardware. But still, let's see how we can do that. So, well, one way of looking at this sort of plasticity is indeed using materials like resistors that are plastic, that do change depending on how often you sweep or how often you fire them. And also you can have multi-states. And people, so there's typically in oxide materials that have this kind of memristive behavior. And these are some very recent results from Twente, where they can have in these oxides resistant states that are like not on-off, but they have multiple, and this depends on the history. So there are ways of doing that, but this is on a single element level. And so this is work from Guus Reinders in Twente, but also partly from Beatrice Nojeda in Groningen. Then there are some maybe potential new materials, because since graphene was discovered 10 years ago, now there is lots of 2D materials, 2D materials that might be actually much more promising than graphene itself, because graphene was, well, indeed, 10 years ago very promising, but, well, the expectations have slowed down a little bit, I must say. I didn't really find any, let's say, real electronics based on graphene. But now people are working on all kinds of two-dimensional materials. And some of these, this is one of this material here, this tantalum selenide, sulfide, and shows that also here you can have all kinds of different states. So this is very tunable. And so this might be a material that is much more useful. And this is something that is even probably, let's say, at least the same way scalable as present-day silicon. Whether it's better or not, I don't know. Then there's other approaches that we have started with, and that is, okay, let's look to this very complex structure here. And then let's go to bed and then try to see how he can model this. And then let's look at a material that might mimic this. Just not so much to make already a new, let's say, computer, but more to trying to get some insight how we could do this in the future. And this is based on real materials. This is a ferroelectric material, and it has domain walls, and these domain walls have this very, let's say, if you have a little bit of fantasy, it looks a little bit like that. And also there, the interesting thing is that you can have various paths of conducting domain walls. But this is also flexible, because you can use either voltages, or you can use just tension. And so you can change these paths, and so you can see if you can make now a structure that can be adaptive, and see if you can learn something about the models. That is the first sort of very modest goal towards actually really materials that can learn. One step actually already in this region is recently done by one of the other colleagues in Twente, and that is he started out with just gold nanoparticles. And these gold nanoparticles are just actually tiny capacitors. They are made chemically, so they are gold with some, let's say, organic shell. And he put them on a chip like this with some electrodes. And at the beginning, they can't really do anything. And so this is a real system, because this is an AFM. So you see basically the scale. So these particles are in the order of, the individual ones are in the order of 10 nanometers. And, but then you start playing with this and playing with voltages, and then you can actually create logical ports from this. And you can actually even rewrite them by changing the voltages again on these electrodes. So again, I have to say that the real programming of this is done off this chip. So it's not a material that learned, but the material can learn, but we have to do it off chip. So this is, but this is something to show that you can actually do certain things that might be useful as components in the future. So this is very recent from Wilfred van der Wiel. Well, tomorrow, Julie will talk about this, that you can actually, from simple elements, already build some architecture. And so I will not mention this, but this is actually, I think, a very big step forward, because this is already something that not only can be made, but can also already do something useful. And so we are also thinking about, indeed, can we use some of these, let's say, models? Bet already mentioned that. And for instance, one of these models looks then a little bit of something that I feel familiar with, because this looks, again, like a magnet, because this is then the spins, and this is the exchange interaction. And we have learned now with our optical manipulation that we can actually manipulate this exchange interaction, so it's not a stiff interaction. But it is something that might be sort of tuned. And so this is maybe for us a possibility to play with that. And so we started playing with this. Oh. And so our question is, can we use indeed magnets to do things like that? And one of the things is indeed pattern recognition. We can do this very well. Everybody knows who's behind this. And, but as we learned already for a computer, this is not so easy. So we have to do this type of pattern recognition, and we could do that maybe with some spin glass. And, well, I had this already in. I didn't know that Bet would also show. But so here you can see the individual atoms at least. So we just started just playing with that. Just having spins up and down, and just using the normal exchange interaction, and then play with the strength, and have this run, and see what kind of patterns you get, and then you can get indeed all kinds of various patterns. We're still working on this, so whether this would be something useful or not, we don't know. But these are actually being done. I was actually surprised, because we didn't do anything special here. This is just a normal RK by Y interaction that you have in a metal, the interaction between spins. And if you do that, then you can generate already all kinds of patterns. And of course, some of these patterns we know on a larger scale, because magnets have, let's say, domain structures. These are domain structures that you find in the visual cortex. And, and these are similar domain structures that you find in magnetic structures. And we can manipulate it and use this maybe to learn something, and at some point, so this is really only as inspiration so far. And then finally, what we hope to do, and this is really an idea that we are start to work on now, is indeed using a combination of these individual spins that interact, but then with our knowledge of, well, we can manipulate the exchange interaction with light, and then maybe we can use these, we can manipulate these weight factors that you have in these models. And, but then we can indeed transport and store maybe information, but without any electrical current. We only use interactions between spins, so there is no current, so there is no Joule heating. And so, because at the end, I really, like I said, I don't really want to understand the brain. I don't want to build one, but I do want to find new ways of manipulating and storing data in a more energy efficient way. Okay, with this, because I'm the last of the day, I think I will stop. Leave some time either for questions or going for dinner in time. So our ambition is really creating materials that learn. It's clear that we are just really start to think about this. We have some first attempts, but there's certainly an enormous amount of things to be learned. And at the end of the day, I don't even know. I don't know what would be the better material to replace this silicon. Is the brain really the best way to be inspired? I also don't know. But it's certainly a lot of fun, and I'm very inspired by this workshop. So thanks again that I can be here. So this is basically our final goal. And I don't want to stop without I thank people in Nijmegen, Twente, Groningen, Utrecht, and also others in Nijmegen. And you for your attention. Thank you very much. I mean, people are actually, I mean, if you look at material science, people are developing materials that self-heal, and which is extremely important. And so this is being done already for a while. It's becoming a very active and also very useful field. But that's not what I'm interested in. And so my motivation is clear. I certainly will push forward with our, let's say, optical manipulation, because I know that this at least will give us some ways of doing energy storage more, information storage more energy efficient. But I'm really looking for, let's say, making a more fundamental step of doing it differently. And for that, indeed, as many here, the brain is an inspiration, because somehow it does things very energy efficient. But maybe it does do only certain things very efficient and other things not. So, as I said before, I'm not even 100% sure, even less now than yesterday when I arrived, whether the brain is the right place to look. But
yes, so you raised this example of the kettle and the
yeah.
And so your reply to that is essentially to say we need to do better, we need to do the storage more energetically efficient.
Yeah.
But the big problem there is, I understand, is really the communication
Yeah, it's not only the storage. No, no.
Dominates the cost.
Yeah.
And so my question for you is, what about communication in materials?
Well, that's a very good point, and that again also there it is like in communication. At the moment, we basically always use electrons. We use electrons basically to store and to transport information. And with this use of electrons, and you have currents, and you have Joule heating, and that's basically where all the energy goes lost. So there are different ways you can improve that. You can use, instead of electron currents, you can have spin waves. And then you have, it's not completely for zero energy, but it is much lower energy. You can also use photons. And there's already a lot of work going on. I mean, photons are basically already used for mass transport because information through optical fibers is being done. What is much harder is to do it on a level of, indeed, computation. And I mean, people have been working on this already for a long time using photons. The problem with photons is that they're very energy efficient. You can indeed code information in an optical pulse and send it with very little loss. But if you want to compute, the interaction of photon with matter is very weak. And that is the challenge. Actually, a little bit of my work is actually working on organic materials and look at their optical properties and see if we can improve that.
Face these energetic problems right there.
Yeah, but the reason, what we do there is actually indeed, and this is why, still I'm coming back to the way we are trying to approach it now, the way we have been able to switch the magnetic domains very efficiently with a femtosecond laser pulse is indeed because we use intrinsically the exchange interaction between the spins. And we excite this because we excite this with a femtosecond laser pulse. So we bring the system in a very strongly non-equilibrium, but we do it on a very short time. So the actual, let's say, energy cost is low, and it's the material itself that does the work, the exchange interaction, which is very strong. It's like 1,000 Tesla. And so this gives us the idea of using light to indeed let the material do the work. And there's still a long shot to real materials that can do it by themselves and learn. But I think there are very good reasons to do it in that way.
I have a related question. So when you were talking about the advantages of this optical writing, how it would be, let's say, with scalings and practical applicability of the femtosecond laser in some hard drive based on that?
Yeah, well, in the hard drive, I think it's actually possible because industry is already developing the next level of the hard drive, and that is HAMR, heat-assisted magnetic recording, in which they implement a laser to locally heat the new materials, because the bits become so small, they need materials with very high coercivity, otherwise the bits are not stable, and because of the high coercivity, they cannot switch it. So I think it's possible to do this, but actually, as I showed, we will be trying in the next 2 years to show a demonstrator, only 8 bits, but an 8-bit demonstrator, where we include the laser, pulse laser, with a MRAM and have an 8-bit photonic MRAM chip. And if we can do it for 8, then it can be scaled.
Okay, thanks.
I had a couple of questions. One is that most of the types of the materials devices you described would be innately two-dimensional. And it does seem to me that the important characteristic of the brain is all this connectivity, which requires probably a three-dimensional structure. So I wondered if you wanted to comment on that. And secondly, since you're such an expert in photons, then photons lend themselves very readily to a three-dimensional configuration. So why don't you just use all optical computing effectively, like holographic storage and interacting photons to build a neuromorphic device?
Yeah. Okay, there are two questions. I mean, I totally agree, and I have no answer to the first question, and that is indeed also the things we do now is still, let's say, limited to two-dimensional materials. Well, with these ferroelectric materials, they are actually, although they're fairly thin films, but they are actually, let's say, bulk properties that are being used there. But there is a big challenge, and I have not a clear idea. I have been thinking about this idea about, let's say, three-dimensional holographic storage in using light. As people have already been trying to do that since the 80s. And apparently, it's not so easy. Because people have been trying this for 30 years. And
I think that my understanding with holographic storage is that there weren't any materials that would work reliably at room temperature. But at low temperatures, it's suddenly possible. So I guess one could build something at low temperatures, which, if it consumed vastly less energy, would still be interesting. Yeah,
no, that's true. That might be possible. If you think about applications of, let's say, in data centers, where indeed a lot of the energy consumption is, then you don't really care. It's like with a quantum computer, right? A quantum computer will use liquid helium. But a quantum computer is not supposed to, let's say, replace my laptop. So it doesn't matter. If it's very good for certain specific applications, then you don't care. So you can do that. In this case, there also may be possibilities to develop, let's say, 3D holographic optical storage. But I haven't really found the best combinations of materials and.
Okay, then maybe I'd ask another question. There was, if you don't mind, there was there was some debate about the True North chip. True North is basically a CMOS chip. We're supposedly working on incorporating some aspects of spike timing-dependent plasticity, and it does use maybe 10,000 times less energy than a conventional CMOS chip. And it was very interesting, this talk by David today about folding. You imagine you could use flexible substrates, and then you could print at much larger scales, used much less energy, and then you could take advantage of this concept of folding to give rise to these interactions on long distances, but also on short. I thought that was kind of an interesting. Couldn't one use plastic electronics then to print, and then maybe even using more conventional field effect transistors in organic materials, and then you fold it up to get a three-dimensional aspect. Do you think that's what might be a viable approach?
That might be, and then you might use something that is indeed, let's say, also being developed, and that is just using a printer, right? A 3D printer, and you can print the whole structure, and then you go in 3 dimensions. I mean, I'm not really.
Yeah. I'd be interested in the answer to the field effect transistor materials. Do you know much about that? Because one, you raise reasons for why biology is so efficient, energy efficient. One of the reasons is that the membrane channels have got a very high charge number, like 5 or 6. So the kind of kappa of the normal transistor is much higher for membranes, operates much lower voltage. And I've often wondered why material science couldn't make a gate of that kind.
No. Well, I have not a good answer. I only know that right now, what industry is really trying to do is indeed bringing those, let's say, switching voltages drastically down. Yes. If you can come down a factor of 10, you gain a factor of 100 in energy. And that is their approach. And for that, they also are looking at what are new material combinations. Yes. Yeah. But for the rest, I'm not really an expert in that.
Thank you, Theo.
Okay. You're welcome.